So, welcome to this session of lecture. We will be continuing with the radiation from the magnetic current source, which we had been discussing in the previous lecture, and we are also going to illustrate the significance of the magnetic current, its relevance and its extreme importance in electromagnetics, particularly in the computation of Green's function for electromagnetic field problems. So, last time we had derived the electric field components for the magnetic current source. So, now we are going to derive the magnetic field components. So, for derivation of the magnetic field components, we will be needing two operations. One is divergence of F and another is grad divergence of F. So, let us compute the divergence of F. So, the divergence of F will be one by r square sin theta del del r of r square sin theta f r plus del del theta r sin theta f theta plus del del phi r f phi. So, now we substitute for the electric vector potentials, the different components of the electric vector potentials. So, we get r square sin theta del del r r square sin theta k L, note that it is capital L, note that it is capital K, k L by 4 pi r e to the power minus j k r cos theta plus del del theta minus r sin theta again k L by 4 pi r e to the power minus j k r sin theta, and f phi is 0. So, that can be written as 1 by r square sin theta that can be written as that can be written as 1 by r square sin theta k L by 4 pi sin theta cos theta del del r of the r dependent terms minus then the theta dependent terms k L by 4 pi e to the power minus j k r into del del theta of sin square theta. And that is equal to 1 by r square sin square, and that is equal to 1 by r square sin theta k L by 4 pi sin theta cos theta using the derivative of the product function. It will be r minus j k e to the power minus j k r plus e to the power minus j k r minus k L by 4 pi e to the power minus j k r to sin theta cos theta. And that will be equal to k L by 4 pi e to the power minus j k r minus j k r by r square plus 1 by r square minus 2 by r square times cos theta. Which finally gives me divergence of f as k L by 4 pi e to the power minus j k r minus j k by r minus 1 by r square cos theta, and that is equation 16. Now, we proceed to calculate grad of divergence of f. So, grad of divergence f equal to A r times del del r k L by 4 pi e to the power minus j k r minus j k by r minus 1 by r square cos theta plus 1 by r a theta del del theta k L by 4 pi e to the power minus j k r minus j k by r minus 1 by r square cos theta plus one by r sin theta f I del del phi k L by 4 pi e to the power minus j k r minus j k by r minus 1 by r square cos theta. So, that is 70. So, now we can calculate the value of the magnetic field. All the r theta and phi components of the magnetic field. So, we know from equation 9 H is minus j omega epsilon f plus 1 by j omega mu grad of divergence f. So, from which the radial component of the magnetic field or the r component of the magnetic field will be minus j omega epsilon f z cos theta plus 1 by j omega mu del del r k L by 4 pi e to the power minus j k r minus j k by r minus 1 by r square cos theta, and that is equal to minus j omega epsilon k L by 4 pi r e to the power minus j k r cos theta substituting for f z plus k L by 4 pi 1 by j omega mu minus j k cos theta del del r of e to the power minus j k r by r minus k L by 4 pi 1 by j omega mu cos theta del del r of e to the power minus j k r by r square. So, we now need to calculate these two terms. So, del r of e to the power minus j k r by r is r minus j k e to the power minus j k r minus e to the power minus j k r by r square, that is minus j k by r e to the power minus j k r minus 1 by r square e to the power minus j k r, and del r of e to the power minus j k r by r square is r square minus j k e to the power minus j k r minus 2 r e to the power minus j k r by r square. By r to the power 4, that is minus j k by r square e to the power minus j k r minus 2 by r cube e to the power minus j k r. So, now therefore, the radial component of the magnetic field becomes minus j omega epsilon k L by 4 pi r e to the power minus j k r cos theta that is the first term plus k L by 4 pi 1 by j omega mu minus j k cos theta then substitute for del r e to the power minus j k r by r, which will be minus j k by r e to the power minus j k r minus 1 by r square e to the power minus j k r. Then again minus k L by 4 pi one by j omega mu cos theta then you substitute for del r of e to the power minus j k r by r square. So, which will be minus j k by r square e to the power minus j k r minus 2 by r cube e to the power minus j k r. Okay. And then on finally simplifying the whole thing, you will ultimately get k L by 2 pi, please verify yourself, e to the power minus j k r cos theta 1 by eta r square plus 1 by j omega mu r cube. So, we call this equation 18. In equation 18, the term k by omega mu equal to omega root mu epsilon by omega mu that is root of epsilon by mu, that is 1 by eta. Similarly, we will get h theta as j omega epsilon sin theta k L by 4 pi r e to the power minus j k r plus 1 by j omega mu 1 by r del del theta k L by 4 pi e to the power minus j k r minus j k by r minus 1 by r square cos theta. And that is equal to j omega epsilon sin theta K L by 4 pi r e to the power minus j k r plus 1 by j omega mu 1 by r k L by 4 pi e to the power minus j k r minus j k by r minus 1 by r square minus sin theta. The differentiation with respect to theta, and this is going to eventually give you k L by 4 pi e to the power minus j k r j omega epsilon by r plus 1 by eta r square plus 1 by j omega mu r cubed times sin theta. So, that is 19, and H phi and H phi will be 0, that is 20. So, these are all the electric and the magnetic field components for the magnetic dipole, and these can be compared with those for the electric dipole, and they will be found to be dual of each other. Okay. So, let us end this topic here. We will be next investigating the significance of the magnetic current and its relevance in the computation of electromagnetic fields. Thank you.